Okay, so for our next chapter, we're actually going to get into complex numbers in trig as well. But for today, we're not actually going to do any trig. We're just going to remember what complex numbers actually are and why they exist. And there's actually some real cool things that go along with complex numbers. Not that you would probably ever do them because you're not going to be a mathematician. But there are some problems out there, and this goes along with physics too, that don't have a solution in the real number system. So there might be, some problem that you can't actually solve dealing with real numbers, but then when you go into complex numbers, there's all of a sudden a solution that actually ends up being a real number. So there's some crazy stuff that goes along with complex numbers. So we actually use them in a variety of ways, but the main purpose for them, or one of the main reasons that we have them, is because we know that we can't take the square root of a negative number, but somehow we can take the square root of a product of two negative numbers that we have. So we have to kind of account for that in some way, so we created this complex number system, or the complex number system exists. So if you remember, the square root of -1 is something that we can't type into our calculator unless our calculator is in the complex number system mode. But in algebra sense, every time we see the square root of -1, we know that it represents some imaginary number I. And then we can take that I and we can square it, which would really mean that we take the square root of -1 and square it. And every time you square something that is a square root, those things cancel out and you get -1. So again, we have this imaginary number that when we square it, when we actually do something algebraic to it, we get a real number, which is kind of crazy that we're dealing with an imaginary number and still get a real answer. So I is a variable that represents a set of all of these imaginary numbers. And for today, again, we're not going to do any trig, we're just reviewing some algebra. So algebraically, when we're simplifying a complex number, we always want to simplify the I out of the radical first. If we can pull it out of the radical, that gives us some really easy manipulation, and then we're just dealing with regular real numbers, and dealing and simplifying regular real numbers is a lot easier. The other thing that you have to remember when you're simplifying any sort of radicals is if you have the square root of two numbers that are getting multiplied in here, then that really just means that we can take the square root of those numbers individually. So if this is the square root of 4 times 5, we could represent it as the square root of 4 times the square root of 5, and then we could reduce that square root of 4 down to get 2 root 5. And I just want to point out that the square root of something that's addition, a plus b, does not equal the square root of a plus the square root of b. That's not true. We can break them up if it's multiplication, but we can't break it up if it's addition like that. Okay, so here we go. We're going to simplify a couple. Again, the first thing that we're going to do is always simplify the I out of the radical. So every time you see a negative here, we're going to pull that negative out and write it as an I. So we have I times the square root of 3. And the same thing here, we're going to pull that I out. So I times the square root of 8. Now we simplify. I and I give I squared. And then we'll have the square root of 3 times the square root of 8. So we can simplify that. The I squared, we know from above, is going to be -1. And then we can multiply those in our root and get 24. Again, that's something that we can simplify down to. So 24 is 4 times 6. We can take the square root of 4. So all in all, we'll pull out a 2, and we have this negative. So -2 root 6 will be our final answer for the square root of -3 times the square root of -8. Okay, so let's do it again. So we have, again, we're going to pull out the negatives in both these. So I'll have an I root 5. And then an I root 10. So we'll get I squared. And then inside our root, I can multiply those numbers to get 50. And then that's something that I can simplify down. I like to look for the biggest biggest square numbers that you can put into that. So 25 is something that I can divide into 50, or that 50 goes into 25 two different times. Sorry, 25 goes into 50, said that backwards, two different times. And I can take the square root of 25 and get 5. I have this I squared here, so that's going to be -1. This will end up being 5 root 2. So -5 root 2 is our final answer. And last one, same kind of idea. We're taking the square root of this fraction. Now this negative out front means we're going to pull out that I originally. And then we're dealing with the square root of 3 over 2. And we've done this a bunch of times where we have the square root of a fraction. So we take the square root of the top, we take the square root of the bottom, and then we have to rationalize. So multiply by root 2 over root 2. And we get the square root of 6 over 2. And then we have an I. And we usually write the I out front of those things, even though you're used to writing variables at the end of our fractions. Or sorry, at the end of our sentence, we usually write i's out front just because if we put the I after a radical, it sometimes looks like that thing is inside the radical, and we don't want to confuse ourselves. So we want to make sure that it's kind of out front so that way we don't mistakenly put it inside our radical. And last one here, we're simplifying the square root, or sorry, 7 over I. And remember I, this might look kind of simplified to you already, but remember I is really the square root of -1. And if we're looking at 7 over the square root of -1, that's something that's not simplified since we have a radical in the denominator. So to simplify this thing, just like you would normally do here, we're going to multiply by the square root of -1 or the square root of -1, but the square root of -1 is just I. So every time you have an I in the denominator, it's like it's acting as a radical, so we need to simplify that in the same way. Multiply by I over I. So on the top we'll get 7I, on the bottom we get I squared. And then again, I squared, square root of -1 times square root of -1 is just -1. So 7I over -1, which will be -7I. Okay, so that's all like the simplification for our imaginary numbers. When we deal with complex numbers have both, so the definition is a number that has a real and imaginary component or part. Sorry, I ran out of room. A real and an imaginary component. And usually we write our complex numbers in standard form, and in standard form we separate the real part and then the imaginary part. So we usually write our standard form as A plus BI. So this represents our real number, and this, since we're dealing with I in it, represents our imaginary number. So in general operations, when we deal with our complex numbers, we kind of treat I just like a variable. So that just means that we add our real components and we add our imaginary components. We add the numbers that don't contain I in them. So these are both our real components of our complex numbers. So we're going to add those, 11 plus 2, that's going to be our A value. And then we have our imaginary components, that deals with 5I and then -3I. So we're going to add those two things. And again, you treat it just like a variable. So you can obviously combine those to get 13, and then you can combine these, 5 minus 3 to get 2, and then we tack on the I. And same thing with multiplying, like we treat it kind of like X, like we would X. There's only one difference at the end, and we'll see what that looks like in a second. So when we multiply, we've distribute everything out, so we'll have 2 times 2, which is 4. 2 times -3I, which is -6I. 5I times 2, which is 10I. And then 5I times -3I, which is -15, and then I and I give I squared. So this is the only difference, because we know that I squared is actually something that turns into a real number. So this, even though it has an imaginary number in it, is actually representing a real number at the end. So we need to change that. I'm going to combine this first. We'll get 4i here in the middle. We need to change that I squared into -1. So that's going to be positive 15. And then we combine our real parts and get 19 plus 4i for our final answer. Again, it's mostly just the same as looking at and combining other things, but we just have to remember that I squared is actually -1, so we have to change it to that real number. On the back is just kind of more simplifications and more realization or deciding how to deal with i's. So this first one, the simplifying 8 plus I over 2 minus I. Remember, this represents some radical, and we just dealt with a lot of things that had like 2 minus a radical in our denominator, and what we did to handle that is we multiplied by the conjugate. So same thing, same idea. Like again, this is like 8 plus square root and 2 minus the square root of I, or -1. And so we did something like we multiplied by the conjugates to get rid of that radical in the denominator. So we're going to do that same thing. We're going to multiply by the conjugate, which is 2 plus I. So on top, we distribute that all out. So we'll get 16 plus 8i plus 2i, which is 10i, and then plus I squared. On the bottom, when I distribute all that out, I'll have 4 plus 2i minus 2i, so the middle terms will cancel out, and then minus I squared. Again, that's what we want when we deal with conjugates. We want the middle terms to cancel out so that we're just dealing with like the first terms and then the last terms. So on the bottom, we'll do that first. We have 4 minus that I squared, remember, is -1. So in the denominator, we'll get 5. And in the numerator, this I squared again is -1. So we'll have 16 minus 1, which is 15, plus 10i. And then again, in rectangular form, what we want to do is we want to split this into a real part and an imaginary part. Right now we kind of have that up top, but we have this denominator, so we're going to divide it out. 15 divided by 5 is 3, and then 10 divided by 5 is 2. So that's our real part, then a, and then bi for our imaginary. So again, if we do have this radical as part of that binomial, which again is like really what I is representing, some radical, we want to multiply by the conjugate. And remember, if it's like a plus b, the conjugate is a minus b, and vice versa. If it's a minus b, the conjugate is a plus b. The last couple examples that we're going to look at is just solving for x, and both these we're going to end up with some imaginary solution. So if we started this like in a real number system, we would solve for x by subtracting 2 from both sides, and then we would divide by 3. And then to solve for x, we would take the square root. And then if we were in the real number system, we'd be like, meh, that's it, that's all we got. Like, we can't simplify any more than that. This is no solution because we have a square root under the denominator. But we're not in the real number system anymore. We're in the complex number system, which means we do have a solution in the complex numbers. So again, we did this on the front. Like, we're really dealing with the square root of -2/3, which means that that negative, we're going to make that, pull that out of the radical and make that I. So we have I times the square root of 2/3. Which we know we can split up the top and the bottom as square root of 2 over square root of 3, and rationalize, multiply by top, multiply by root 3 over root 3, and get I root 6 over 3 as our answer. Don't forget though, because I did forget one thing for this one, when I take the square root, I always have to have a plus or minus. So in all of these things at the end, we're really dealing with a plus or minus I square root of 6 over 3. So don't forget that. That's really important. This like x squared, don't forget that we need to use a plus or minus when taking the square root. And we'll see that in this one too, although this one is something like some trinomial you might want to try to factor. This one we could end up factoring, but it's a little bit harder with like our factors in this case because we would have to factor it into imaginary components. So instead what we're going to do is we are going to use the quadratic formula to solve. So we're going to solve for x by using the quadratic formula. This is my a, my b, and my c value. So opposite of b would be positive 6 plus or minus the square root of b squared, negative 6 squared, minus 4 times a, which is 9, times 6, or 5, which is c. And that's all over 2 times 9. Again, I always like to type all this stuff underneath the square root into my calculator. And if you do that, you'll have 36 minus 36 times 5, which is 108, I think. So that'll end up being negative 144 over 18. And we can take the square root of 144 and get 12, but we have negative 144, which just means that we're going to pull the I out. So this will be I times the square root of 144. And the square root of 144 is 12, so 6 plus or minus 12i all over 18. And then we want to separate this again into an imaginary part and a real part. So I would split it up now as 6 over 18, which is 1 over 3. And then 12 over 18, which we can reduce down, divide the top by 6, divide the bottom by 6 to get 2 over 3i. So again, we have those two solutions, 1/3 plus root 2/3 I, and then 1/3 minus 2/3 I. So same thing as we solving the quadratic formula, it's just that we have i's in our answer now. Okay, and the very, very last thing that we're going to talk about is handling different powers of I. So far we've looked at I squared. We know that that thing is -1, and we know that I to the first power, which is just I, that's the square root of -1. But what we haven't handled is any greater powers than that. So any number, let's handle our I to the 0, any number to the 0 power, if you type that into your calculator and do some tests, you'll end up seeing that that is just 1. So far we have 1, we have square root of -1, and then -1. So I cubed means that we're going to take I squared and multiply it by I. That's how exponents work, is we add the exponents to get to our higher exponent, which means that I squared we know is -1, and I to the first power is the square root of -1, which is just I. So -1 times I. So that means I to the third power is just -I. Okay, well, I to the fourth power then is I squared times I squared. So we add those up to get 4. I squared is -1. I squared is -1. -1 times -1 is just +1. And then for I to the fifth, that would be I to the fourth times I, so that we could add those up to get 5. Well, I to the fourth we just found out was 1. I to the first power is just I, so we'll call that I. I to the fourth is just 1, and this is just I, so I to the fifth power is just I. And I to the sixth is I to the fourth times I squared. And notice I'm trying to keep my values even, because those are easier to deal with. I to the fourth, I know is 1. I squared is -1, so 1 times -1 is -1. And so on and so forth. We skipped I to the seventh, but we could do that. I to the seventh would be I to the sixth times I. I to the sixth we know is -1. I is just I, so this would be -I. And then we could repeat and go from I to the eighth, which is I to the fourth, times I to the fourth. And we know I to the fourth is 1, and I to the fourth is 1, so this would just be 1. So you'll notice that we have this repeating cycle that goes on. So I'll have 1I, -1, -I, 1I, -1, -I, 1I, -1, 1I, -1, -I. So it'll repeat with cycles of 4. And mainly it repeats with cycles as 4 is because at I to the 4th we get back to where we started from. Okay, so if we're trying to come up with like a large power of I, like if I were looking at, let's just try I to the 16th. Well, I know again, like I to the 16th is I to the 8th times I to the 8th, and I to the 8th is I to the 4th times I to the 4th, which is I squared times I squared, and I squared, and I squared. And I squared is 1, so all these things would just be 1. And then once we have like one starting point, like notice 16 is divisible by 4, and it goes into that evenly. So once we have one spot where we know that that's the 4th, then it's really easy to find out like I to the 17th because we already have a starting point. And if we know like it goes in that order of 1, I, -1, -I, then I to the 17th is just I, and then I to the 18th is just -1, and then I to the 19th is just -I. Like we can go in that order. So if we're looking for like really big powers of I, like the ones below, we need to divide the power by 4, and the remainder is the exponent. So I'll demonstrate what I mean by that for this one. I to the 275th power. So that means that we're going to take the 275 and divide it by 4. Okay, we type that into our calculator. We get 68.75. So that means it goes into it like 68 times evenly, and then we have this like 0.75 left over, which that is 3 over 4. So that means that our new power that we have, like this would be 3/4 of the way in our cycle. So we'd be at 0, 1, 2, and then 3/4 in a way of our cycle. I guess it'd be 1, 2, 3, and then 4. So 3/4 would be at this new exponent. So like really the 3 is going along with our new power. So this would really be equivalent to I to the 3rd power. And we know I to the 3rd power is I squared times I. That's really all you need to remember. So that means that it's going to be -I. Okay, let's do another one. So 518, we divide it by 4. We get 129.5. This 0.5, remember, it means it doesn't go in evenly, so it's not just 1, but this 0.5 is going to be 1/2 or 2/4 of the way through our cycle. So if we start with I to the 1st is our first part of our cycle, then I squared, that's going to be the second part of our cycle. So this would be then equivalent to I squared, which we know is just -1. So we can kind of figure out like where the cycle is starting again. Like this goes in this many times, so we're back to our starting point of like 1. And then if it goes into like an additional time, it'd be like 0.25, an additional time would be 0.5, an additional time would be 0.75, and then a whole number would be back to where we started point, which is just 1 again. So again, last time, if we take 137, we divide it by 4. This time we get 34.25. That 25 means that we are 1/4 of the way through our cycle. So if we're starting at like 0, 1/4 would be I to the 1st power, which is just I. So like this fractional part becomes our new exponent, and then we can simplify from there.